Hello, so in this video, I wanted to have a brief discussion using some of our market-based supply and demand frameworks to better understand the issues surrounding open access resources, or some people like to call them common pool resources. And so let's go ahead and share the screen to start this discussion. Okay, so the basic idea here is that we are dealing with a special type of resource that goes by the name of an open access resource. And it has open access resources have two qualities which interact to create these problems for markets to naturally reach, we'll say, economically efficient allocations. And so either one of these things alone is sort of interesting, but when you combine them, you kind of get the perfect storm. And that is non-excludability and rivalry. And so just as a reminder, non-excludability just means that we have a resource out there and anyone can use it and no one can prevent anyone else from using it as well. And so we can't exclude anyone from using the resource. And on top of that, we have this resource having this function of it being rival, in that if someone is using the resource, they are going to prevent someone else from realizing as many benefits from that resource as they would if they were alone. So a good example of this is if you have a finite resource, as more and more people start using it, there's less and less that's available for others to use. And so there's lots of examples of resources that are like this. We've got things like, examples like, deep ocean fisheries. This is an example where you can't limit boats from going out into these kind of deep areas that maybe no one claims any ownership of. And so anybody can fish there, but yet there's probably still a finite population of fish available there. And so those two things, the non-excludability and the rivalry, end up playing a role. But you can also think a little bit more locally, and you can think of something like, let's say, interstate highways at rush hour. And so in these cases, we assume that anybody can get on the highway, and at rush hour, we actually start feeling the limited capacity, so that as someone else gets on the highway, it increases congestion and makes the next person's benefit less than the benefit realized by the person who got on the highway originally. You might also think of something like public Wi-Fi with low total bandwidth or throughput availability. So you might say, it's great that I can go for a walk in the park and I have access to city Wi-Fi, but if that Wi-Fi has low bandwidth and if there's a lot of people in the park, then you start noticing that as more and more people connecting, then everyone's speed ends up getting so slow that you might as well not have any Wi-Fi at all. And so all of these we can view as open access resources, and it can be a significant problem to maintain the kind of quality of those resources, and they can lead to exploitation, over-exploitation, in the case of things like fisheries, total extinction of those fish. So let's try to understand this from this supply and demand perspective to see what's going on here. So before we focus on open access resources, let's imagine we took one of these resources and we could manage to totally privatize it. So there would only be one individual or one firm that would have total decision-making authority about the resource. And so let me draw a curve here. And so this is going to be a little bit different. So normally I would just draw one of these quantity and then these marginal quantity graphs when I do supply and demand. I'm actually going to start out by actually drawing the total benefit and cost, not the marginal benefit and cost. And then underneath that, I'll end up drawing the marginal benefit and cost. So I don't want to throw you for a little bit, but I just want to say, you know, up front, it's going to be a little bit different. So let's do that total benefit first. So I'll draw that here. Maybe this far. All right. And so as is usual, this is Q. This is the quantity of that resource that is currently being exploited. But up here, instead of doing dollars per Q, I'm just going to do dollars. And so this is actually going to be the raw benefit and raw cost, total benefit and cost, I guess I should say, for the amount of exploitation I have here. And so I am going to, let's see, how many did I draw here? It looks like I've got, I'm going to say that I'm going to make some marks here at about the halfway point. And so, so what I'm saying is, what if I've got a resource that once I start exploiting it, I get some benefit from that exploitation. That benefit is going to peak at some point. But then if I overexploit it, then that benefit will end up being reduced to the point where if I exploit all of it, then I get no benefit out of it whatsoever. And so you could imagine this like in the case of a fishery, you could imagine that over on this side, if I'm not exploiting the fishery, I got no benefit out of it. But if I fish the entire fishery to pull every single fish out of there, then I am going to end up having effectively no long-term benefit out of this fishery. I'll use it all up. It'll be a limited resource that I will have burned right through. And there will be some maximum sustainable yield that'll be in between where I get the maximum benefit, raw benefit, you know, not considering cost, or maximum gross benefit out of that fishery. And so we'll get this hump-shaped graph like this, where with more exploitation, you get more benefit, it peaks, but then after that peak, then the benefit actually falls off with additional exploitation. So something that looks like this curve here. So I'm going to try my best to draw a parabola. I will probably fail at drawing a nice looking parabola, but hopefully you get the picture. I'm going to try to make it peak right around there. So maybe it goes up. It hits there, and then it comes back down. And with all luck, it intersects there. So imagine it's about this kind of symmetric parabola around that point there, where we've got this, you know, this maximum yield. And if you'd like, you can think of this as dollars per year. So as an example, dollars per year, if that helps you. And so the idea being that if I overexploit this thing, if I just take all the fish out in the first year, then on average, my dollars per year goes to zero. So that's where this kind of hump shape comes from here. All right, now, if I am exploiting this thing alone, then I can keep track of what my total cost is per unit of exploitation. So I know how many trips I go out of the fishery, for example. You know, I know how many, I generally know how much effort that I've put in order to try to get this benefit out. And we're going to assume that there's a constant marginal effort rate. And so basically this is the total effort curve is going to look like a line. So if I then draw a line here, so I can say, well, let's draw something that looks like this. Oh, I meant to draw that as a straight line, apologies. All right, and so, and let's just annotate this so we all remember. So this here is the total benefit. And I'll abbreviate that TB. And this here is the total cost, which I'll abbreviate TC. Okay, so if I am the only one having access to this resource. This, so we're considering this to be a private good. I am the only one that has access to it. So it is excludable. I can keep anyone out, and it's rival. So, of course, the amount of use I get is going to take away from the amount of use I could get later. And so these things together, when I need to make my decisions about exploiting this resource, then I know that my exploitation, or that my benefit, is going to be the net benefit of my benefit minus my cost. Or to put another way, every time I put in another marginal unit of effort, I can keep track of how much marginal cost I've increased. And as I go up and up in my steps of effort, I can keep track of what the return I'm getting for that increase. And so for my first unit of effort, then I get a major jump in benefit. And I can say, wow, that jump in benefit is much bigger than the jump in cost. But for my second unit of effort, then I get maybe less of a jump. And then for my third unit of effort, I get less of a jump, and so on. And eventually I get to a point where there is a point where I am going to choose to stop exploiting this resource, because every additional unit of exploitation is just going to be more costly, and I'm not going to get enough benefit out of it. And so it's like taking a sponge, and you've wrung that sponge and dry, and there is moisture in there, but the amount of effort it takes for you to get more moisture out of the sponge is not going to equal the tiny little benefit you get from making that sponge just a little bit drier. And we know that that point is going to happen where, so I'm going to paste this here. So I'm going to try here in a second. Okay, there. If I take this line, I should be able to find a point on this curve. And I may end up erasing some of this, but I will find a point on this curve whose tangent line is parallel to my marginal cost curve down here. And so there's a point right here, and here's its tangent line, and that tangent line is parallel to that, and that point is going to be the efficient exploitation value for this resource. And so just to clean this up, let me zoom in on a little bit of here and then erase some of this line to make it a little less distracting. And over here, do my best. Okay, that looks good, I think. And then this tangent line, this point is, say, right around here. So if I zoom back out, then what we see is that there is some point around here that is the efficient level of extraction from this resource. So that maximizes, to put it another way, that point right there maximizes the net benefit. So this line that I just drew there, the net benefit, so keep in mind that's like the distance between the cost, the total cost, and the total benefit, the distance between there. If I were to grab that thing and swing it around, so if I were to grab this whole arrow here and move it around, then as you see, if I move it to the left, then it ends up, I can't fit it in there. So there's no room for it to move to the left. And in addition, if I were to move it to the right, then it also starts getting crowded out by this line here. So even though the benefit keeps increasing, because the benefit increases at a rate that is shallower than the costs that increase, then the net benefit, which is the difference between these two, ends up getting smaller here. So it gets smaller as I go back this way, and it gets smaller as I go back this way. So this here, that that is the optimal allocation. That is where we want to be, right here at Q star. That's the, so I'm going to write, I can write net benefit next to that. Okay, and if I want to put this back in my supply and demand terms, then I can go and draw our favorite curves here down below. So, and I won't maybe draw this as large. Maybe I'll stop here. And so roughly speaking, then this is going to be a little bit compressed, but I am going to have a marginal benefit curve, which I know is going to hit 0 benefit here. And so I can draw a line that starts at some, and I guess I should label these axes. So this is the dollars per Q that we're accustomed to. And so I am going to have a marginal benefit, which starts at some point, and then it is just going to be a straight line, which I'm going to pierce through 0 at this point here, and then keep on going. So that wasn't quite perfect. Let me try that one more time. I am just not doing so great. All right, well, I hope you can, well, maybe I'll just cheat a little bit here and just grab that line and move it a little bit. Okay, how's that? And if I make that dot a little bit bigger, it'll look like I actually meant to do that. Okay, so the idea here is that that point right there, where the marginal benefit, where the marginal benefit goes to 0 is exactly the point where this the total benefit curve goes flat. That's the maximum point there. And anything after that, the marginal benefit has now become negative. And so any additional unit of effort you put in is actually going to take away from your benefit. That's what is being drawn here by this marginal benefit curve. Now the total cost curve, I can now draw the marginal cost curve, which is the derivative of that line, and that's just going to be a constant. It's going to be a straight line at whatever the marginal cost is. So if it's ships in a fishery, it's like the cost per ship. And so I could draw that there, and that just needs to intersect, that will intersect at this point. Oh, meant to. And this is all eyeballed and approximate, but that was the intent there, was for that to intersect at around Q star. And so I can then put this thing here, and I can say that so if I would have started with the marginal cost curve, so I'll label these curves for you. So this here is the marginal benefit curve, and this down here is the marginal cost curve, and it's constant. And so for a private good, then the marginal benefit curve is going to be my demand. My marginal cost curve is going to be my supply. Those demand and supply are going to come into equivalence at the socially efficient allocation, which is that Q star. And so the price of this good would just be equal to the marginal cost. So that would be the P star over here. And everything would be good, so to speak. But that's for the private case. Now, what happens in the open access case? So for a private person who controls all of the exploitation, then they know that they already received a certain amount of benefit here, and they know that every additional unit of benefit is not going to increase at a rate that will beat the increase in their personal private cost, and so they stop there. But now let's imagine that this resource that was privatized now becomes open for anybody to be able to use. Well, then what's going to happen? Well, everybody else out there just has to make a decision. Do I go and put my boats into this open access fishery, or do I go somewhere else? So they basically have two decisions. Do I enter the fishery or not? And so what determines whether they enter the fishery? Well, basically, if there is any benefit to entering the fishery, that is better than not entering the fishery. So the basic idea here is that the marginal benefit of entry is positive and the marginal cost of entry is zero. So you can view it that way, is that for the open access case, then really we're saying is, do I enter the resource? And the marginal benefit of entry is just going to be equal to basically the current total benefit minus the current total cost. And the marginal cost of entry, because it's non-excludable, is equal to zero. And so we know that individually, the individuals that kind of respond to their internal supply and demand pressures are going to view any benefit whatsoever as kind of a demand curve, and then their supply curve is effectively going to be equal zero. It's going to be free. So this is basically saying free entry. And so long as this means, like, so long as TB minus TC is greater than zero, then you enter. Or in other words, so long as TB is greater than TC, you enter and use more resource. And so what that means is that in the open access case, you might have had a private user that stopped here, but somebody else who hasn't gotten any benefit out of it says, oh, well, you know what? I can now get a little bit of benefit out of there. So why don't I go and put my boat in that fishery? And so they are then going to increase the usage. And then someone else is going to say, well, there's still a gap here, so I'm going to put mine in there. And then they'll increase, and so on and so forth, until eventually you end up getting the open access equilibrium, which is over here. And so this, which I'm going to call QOA, is the level that you would expect the resource to be exploited under the open access condition. Because at this particular case, then finally you've squeezed that sponge out to the point where it is totally dry, and so, I mean, I guess saying totally dry is taking this metaphor a little bit too far. It's not quite totally dry, but at this point, there really is zero benefit that anyone else can get out of this thing. And so this total cost, so this open access condition is the condition where total benefit is equal to total cost, whereas the efficient condition that we're used to is where marginal benefit is equal to marginal cost. Okay, so what damage is done by that? Well, we can go and do our marginal damage calculations here, and those of you thinking this through might have already figured this out. So I know that the area underneath the marginal, in between the marginal benefit and the marginal cost curve to the left of the efficient point, that there we view as the net benefit. So that right there, this area that I've highlighted in yellow is equivalent to this net benefit right here. Now, the interesting thing is that the area to the right of this here this here is the deadweight loss, the DWL. So this is by operating, I'll say, at the open access condition. And if you look at that, I know that, you know, I just kind of hand drew these things, and so things don't come out perfectly, but I hope you can see that the gray area is equal to the yellow area. So this, in the yellow area, this was our net benefit. And at the open access condition, then the net benefit from the kind of efficient, so maybe I'll do net benefit star, the net benefit at the efficient condition is equal to the deadweight loss. But remember that the social welfare at the open access condition is going to just be equal to the net benefit, the yellow area, minus the deadweight loss, which is equal to 0. And that makes sense because what we're really saying here is that the net benefit at the open access condition, that's what we mean by the social welfare. And as you can see, the distance between the two curves is equal to 0 exactly at the open access condition. So that is really the problem with open access resources, open access goods, or common pool resources when your individuals in the common pool is a very, very large number of individuals, is that the open access condition ends up destroying all social welfare. You end up basically taking what used to be something that could give some benefit to society, and the deadweight loss is tremendous. It's extreme. It's maximal. You end up making the resource basically as good as it not having the resource. Go back to our examples from before. We talked about public Wi-Fi up here. You know that public Wi-Fi, when there's too many people on it and it has limited bandwidth, basically ends up grinding to a halt, and anybody has to switch back to using their cell phone plans or just not using Wi-Fi whatsoever. You know, highways at rush hour might be gridlock. So in the best case scenario, the highways at rush hour will be as fast as the side streets. And so in that case, you may as well just use a side street. It kind of removes any benefit of the highway, and it can even be worse. Like you can imagine highways at rush hour might even be slower than the side streets. And then similarly, deep ocean fisheries, what you can end up doing is if you think about the dynamic process of regeneration, it turns out that in a fishery, if you go beyond the so-called maximum sustainable yield, then the fish won't be able to reproduce fast enough to keep the fishery going. And so basically going anywhere over this maximum sustainable yield guarantees that the fish will eventually go extinct. And so at that point, you may as well not have had any fish. So that's the major problem with these open access resources, is that people just following their own individual benefits. You know, the things that are here, I mean, the tragedy of the commons here, like what do we mean by tragedy? Let's just put that down real quick, is that the tragedy here is that individual rationality or individually rational choices to enter. And so that would be that the total benefit is greater than total cost, so I may as well enter this resource, lead to collectively disastrous outcomes. So every individual was really just doing what was best for the individual, but for the group, it's a problem. And so that is why these things fall under the category of collective action problems. And collective action problems have to be solved with things that motivate people to start to that basically motivate people to start recognizing the negative externalities they're putting on other people. So in reality here, the reason this is an incomplete market is that everyone who enters is going to pick up a benefit for themselves, but they are going to reduce the benefit of everyone who has already entered. And so that's where there was a negative externality here there. So the negative externality, I guess I should write that here, the negative externality is the effect new entries have on existing benefits. And so how do we internalize this negative externality? Well, there's a number of different ways you can do this, but they all basically come down to getting rid of non-excludability. So if you have a highway, maybe you put a toll road up there. So people have to pay to get onto the highway. By paying to put onto the highway, then if you charge them enough, then they can end up paying the externality that they otherwise would be forcing other people. So they're basically paying for the benefit that they're reducing from other people. And by including that in their own decision making, then it's going to reduce the number of people who are just entering that highway. Public Wi-Fi, well, if you make them pay for it, that's another way to do it. So there are a number of different ways that you can solve these collective action problems, but they're all going to somehow relate to introducing some form of exclusivity to the access. And so either only those who can use the resource who have paid for it, or maybe you're going to manage to privatize the resource and then have a gatekeeper deciding who gets to use it and who doesn't, and all of those sorts of things. So it's the excludability that's really the problem here. There's lots of resources that have rivalry, but if they're privatized, that usually takes care of them. So the closer and closer you take a rivalrous resource and move it towards a privatized resource, a lot of times you get rid of these problems because you end up effectively internalizing this ugly negative externality. All right, I hope that helps. Have a good day.